This is the second part of the Using and Expressing Measurements lecture. This will be on significant digits. Be able to define accuracy, precision, accepted value, experimental value, error, percent error, and significant figures. Be able to list the rules for significant figures. Be able to add, subtract, multiply, and divide numbers while maintaining significant figures, and be able to calculate error and percent error. First off, what are significant figures? They are a means of expressing how accurate a measurement is. Well, first off, what's accuracy and what's precision? Accuracy is how close you are to an actual value that you know. So here's an example with low accuracy and low precision. Numbers are just all over the place. With high accuracy, the average is going to be the center of the bullseye, i.e. the value that we know it is. So if a scale was going to be calibrated, it will be accurate. But if it's easily disturbed, you might actually end up getting different measurements around that central accurate value. So precision is going to be how close the measurements are to each other, how reliable they are. So if the balance is not disturbed and calibrated, that can be precise but not necessarily accurate at all times. So high accuracy, high precision is the goal. That's when everything is around that central value and the measurements are very repeatable. So what do I mean by a central value or accepted value? Accepted value is the value based on reliable references. So this is when someone else has also done the math and has determined what the value is. This is what calibration is. You can purchase items that are exactly 200 grams in mass. That is an accepted value that it is 200 grams. If you were to put this on a balance and get a value of 210 grams, that's your experimental value. That's the value you are getting from the lab, the value when you actually measure something. And the error is going to be the difference between the two. In this case, the error is going to be 10 grams. You had a 200 gram weight that you weighed in at 210 grams. That's going to be an error of 10 grams. And if it was 190 grams that you weighed, that would also be an error of 10 grams because an error is an absolute value. So there's no negative error. The percent error is the error divided by the accepted value and multiplied by 100. So you're 10 grams off. 10 divided by 200 is 0.05, and that is multiplied by 100%. That is going to be 5% off, and that's going to be your percent error. Significant figures are the measure of all the known digits plus one estimated digit. So if it was only accurate to 100 kilograms, we'd have to estimate it at either 0.8 or 0.9 of that accuracy. If it was accurate to 10 grams, that would either be 80 kilograms or 90 kilograms. So we would add one estimated digit and say it's probably 85 or 87, somewhere around that area. But that's going to be your significant figures, are all known digits plus one estimated digit. So let's see some rules for significant figures. First off, significant figures apply only to measured data. So it's only going to be things that we're actually measuring. All non-zero figures expressed in a significant figure are significant. All zeros between non-zero digits, so 1.07, that zero is significant. Decimal points are going to define the significant zeros. If the decimal point is present, all zeros to the left of the last non-zero digits are significant. So 8.500 liters has 4 significant figures because we have calculated it out to 8.500. We're looking at that and that's very exact. If a decimal point is not present, no trailing zeros are significant. So 1800 grams means we've measured this only to the 1 and the 8. The 00 are just placeholders, and those are not significant. So those are going to be non-significant figures. If a decimal point is present, none of the zeros to the left of the first non-zero digit are significant. Those are also placeholders. Counted numbers and defined quantities have infinite significant figures. So if there are 8 students in a classroom, that's 8.0000000 because we know there are no fractional students. So one of the rules we have when we are adding, multiplying, or any of this is not inventing new significant figures. If we add 2 measurements, we're only as accurate as the least accurate measurement, which means we're only as accurate as the measurement with the least number of decimal places. So 8.500 liters plus 1.2 liters is going to be 9.7 liters. It's not 9.700 because we don't actually know that 1.2 is 1.200. It could be 1.208 or something like that. We don't know because we are not measuring it exactly enough. So we have to be conservative and only use the minimum number of decimal places. When you are multiplying two measurements, it's only as accurate as the lowest number of significant figures. That is why we have you practice counting the number of significant figures. So it's only as accurate as the least accurate measurement. So if the radius of the Earth is 6378 kilometers, what's the volume? Well, we can calculate it as 1.087 times 10 to the 12th cubic kilometers because we're cubing it there and we have four significant figures.